In this question, you're being asked to produce a arrow pushing mechanism leading to the expected major product of this reaction. So in a previous example, we've already identified the substrate and the nucleophile, so we want to do that again because we want to know what the expected major product is. I also want to mention that we are in lecture 14, which is the SN2 lecture. Later on, in some later lectures, we're going to talk about some competing reactions, which means whenever you're evaluating reactions, you're not always just going to be able to say, hey, this is SN2. There's going to be some competing reactions. But since we haven't talked about those yet, I'm pretty much providing examples in the lecture 14 that are just going to be SN2, because that's where we are right now and we haven't talked about the competing reactions. Just be aware that that is coming. All right, so we've already identified in a previous example using these same reagents that this is the substrate right here, and the bromine is the leaving group of that substrate. This species right here is the nucleophile, specifically nucleophilic at this nitrogen atom here. So what I'm going to do here is I'm going to redraw this substrate. And I'm also going to draw in all of the electrons. There's a reason I'm doing that, because when you're being asked to produce a mechanism, you are being asked to explain how these reagents become the product. That's your job with a mechanism question. You're explaining, how did electrons move? How did bonds form? How did bonds break? So you want to show all the electrons typically when you're doing a mechanism. All right. Let me also draw in the nucleophile. I'm just going to draw in the nucleophilic portion of that. So I'm not drawing in the sodium cation because it's not really a player in this reaction. All right, so we have our nucleophile, we have our substrate. We have to remember that this carbon, which I'm dotting in red, that is the electrophilic carbon. That is the carbon with the buildup of positive charge. Because the bromine is more electronegative, it is pulling electron density away from that red carbon, which means that red carbon, if it's positively charged, it's susceptible to attack by things with negative charge, things like a nucleophile. So what's going to happen here is those electrons on that nitrogen are going to attack that red carbon. They're going to form a bond. But carbon already has 4 bonds to it, so something has to leave. Well, the best thing to leave are the electrons between the carbon and the bromine, because when those leave, the bromine ends up with that negative charge. And the reason that's the best leaving group here is because that bromine, it's larger, it has more space, it's more polarizable, it can handle that negative charge better than the other possibilities. The other possibilities are the hydrogen could leave with the negative charge, but that is a very, very strong base, H-. It's very unstable, so it's not going to leave. This carbon or this carbon could leave with the negative charge, but carbon with a negative charge is a very strong base/nucleophile. They're also really unstable. So the thing that leaves is the most stable entity, which in this case is this bromide ion. But that's not really what we're after here. The major product in this case is going to be this species right here. Now, I drew this in a specific way. Let me dot that red carbon so we can keep track of it. I drew this in a specific way because we have to remember, in an SN2 reaction, the nucleophile approaches the electrophilic carbon in a specific way. And the way it does that is from the backside, which simply means the side opposite the leaving group. So since in this substrate, we have the leaving group going into the paper and the hydrogen coming out of the paper, that means the nucleophile approaches nearest the hydrogen. So it means the nucleophile approaches from outside of the paper, which means that hydrogen, those electrons between hydrogen and carbon, they're going to repel into the paper. And that is why over here in the product, we have the hydrogen now on a dash, and the nitrogen came and added to that red carbon from outside of the paper. What this means is, when you're doing these reactions on a stereocenter, you will oftentimes get an inversion of the stereochemistry. So if we look at this red carbon here, the configuration of that carbon is S. If you don't know why that is, go back to the lecture on stereochemistry. The substrate started with an S, the nucleophile came in and added, and in the end, there was an inversion here. That stereo center is now R.